Hi, my name is Petrus Swissler, and today I am presenting Reactive Build, environment adaptive self-assembly of amorphous structures. Self-assembly is a set of behaviors you sometimes see in social insects, in which many insects will join together in order to form useful structures. Such structures include cantilevers, chains, towers, and bridges. These structures seem to be formed from interacting with the natural environment and seem to serve the purpose of enhancing swarm capability. The promise of enhancing swarm capability has driven research into robotic self-assembly. Of course, robots are robots and insects are insects, and so there are differences between the approaches that each take, likely stemming from the fact that robots often operate in controlled laboratory environments, whereas insects operate in nature. The first big difference that I'm going to be looking at in this presentation is that of how the structure is organized. In the case of insects, it seems to be the case that they're grabbing on with their legs, their pincers, basically wherever they can. The resulting structure has little in the way of discernible organization and is therefore referred to as an amorphous structure. In contrast to this, most robotic systems rely on attaching at very specific locations, thus resulting in highly latticed structures. The problem with highly latticed structures, however, in the context of large-scale self-assembly, is that you may run into issues where the robot cannot actually build any further. Consider, for example, tolerance stack or gravitational loading. These might cause deflection such that a given robot cannot complete the structure. Also consider what happens if you're growing from two locations at once and meeting in the middle. If you have a lattice structure, you're going to have to align the two sides very carefully prior to actually starting construction. Of course, nominally you want to operate in arbitrary environments, and so this is problematic. The second and final big difference that we're going to be looking at here is how the structure is defined. Now, for most robotic systems and robotic self-assembly algorithms, what is the case is that a human operator will give an a priori structure, say, "Hello robots, please make me a wrench," and then the robots will seek to make a wrench. In nature, the closest analogy to this is where you have cells growing into complex organisms. So for instance, you start out with 2 cells and you end up with little baby Petrus. However, the sort of structures that are built by social insects do not seem to have this overarching plan from the start. They seem to be reactive structures. So they are solely based on the insects interacting with environmental factors. There are relatively few examples of these sort of reactive structures in robotics, which is somewhat surprising given that there are many potential benefits of this approach. So, for instance, you are not tied down to a specific solution to an environmental problem. Thus, you don't have to worry about making the exact shape, and so you don't have to worry about the localization problem. You don't have to communicate in order to perform that localization. You, of course, don't have to keep in mind the target structure. And so there's somewhat of a gap in the literature where there are few algorithms that can actually make reactive structures and also few that can form amorphous structures. In Mellenbrick et al., they formed cantilevers using local force information in order to guide self-assembly. In Malley et al., Aceton Robotica, they used robot traffic effects, so robots bumping into each other, in order to form bridges. This one was amorphous, whereas the previous one that I mentioned is latticed. And so that brings us to Reactive Build. So like Mellenbrick et al., the robots will be using force in order to guide construction. But what sets Reactive Build apart from these other two examples is, first, it's going to be presented in 3D. Second, we are going to be considering both single origin and multi-origin structures. And we are also going to be looking at using the exact same set of behaviors in order to make different types of structures, whereas the other two concentrated on a single type of structure. So what is required for a robot to build using Reactive Build? Well, the requirements are relatively minor. So first, it has to be able to climb the environment and also to climb its peers. Second, there has to be some method of communicating with local robots, neighboring robots. There's few messages, and these are all just integers. The robot must be able to sense local forces. So if I'm pulling on the leg of a robot, it must be possible for that robot to detect it. And finally, it must be possible to detect the direction to some goal position. Imagine that I'm hanging a light bulb over here and the robot has to move towards the light. Note that there's no requirement for amorphous structures. However, this will work for amorphous structures, as we'll show later. Within Reactive Build, there are going to be robots that have two different roles. There are moving robots, which are the ones that are actually moving and climbing on the structure. And then there are structural robots, which are the robots that are actually part of the structure. We assume that once a moving robot joins the structure, it permanently becomes a structural robot. So there's no self-disassembly. Also, because we know from Malley et al. That traffic effects can have big impacts in the process of self-assembly, in order to simplify analysis and evaluation of this algorithm, we're only going to concentrate on the case where there's one moving robot at a time. To actually explain Reactive Build in the paper itself, I have a more formal sort of explanation, but here I'm going to present it in the form of a motion comic. So let us consider a moving robot, shown here in purple, that wishes to climb the structure. So the first rule it must follow is that it must move towards the goal location. And so it evaluates which of its two legs is closest to the goal. In this case, it's, of course, the forward one. And so it moves around that circle, taking a step towards the goal. Back leg was previously closest to the goal, front leg now closest to the goal. And so it continues motion using this rule until at this point, the circle that it just moved around, last time was closest to the goal, is also now closest to the goal. And so if it were to move towards the goal location, this would result in backwards motion. So we introduce this other rule where if a robot would move backwards, it transitions from being a moving robot to being a structural robot. Now let us say that the addition of this robot has resulted in increased structural stresses down here, and this robot has detected them. Well, it is going to start recruiting structural reinforcement. We'll talk about the relationship between recruitment value and the measured force, but for now, just know that it's monotonic. So this one has detected the force, and so it must output a recruitment value. And every single robot actually has this sort of recruitment value, but by default, it is 0, meaning that it is not recruiting. Any neighboring robots that see a neighbor with a recruitment value will propagate and decrement this signal. So we see that this robot has sent out the 3. This neighboring robot sees the 3, decrements to 2. Across the robot, decrements to 1. And then, of course, this one sees the 2, decrements to 1. Then it kind of peters out to 0. All right, so now we have another moving robot that has climbed onto the structure. And much like before, it moves towards the goal. But at this point, it detects that a robot that it has just climbed onto is recruiting. And so now this robot becomes recruited into the structure before it would take that backward step, and so it stops and joins the structure. Now we say that this robot over here, the structural stresses have reduced, and so it recalculates the recruitment value, and let's say it goes from 3 to 2. because of the way that the propagation and decrementing of recruitment values works, this recruitment radius naturally shrinks, as you see here. As I mentioned before, the relationship between recruit value and the sensed force is monotonic, but I will kind of talk through exactly how it's calculated right here. So of course, you're always going to have some sort of structural force just naturally, and you don't want to be recruiting all the time. And so you have a threshold force below which you're simply not going to recruit, right? You just accept that there's some level of structural stresses that you're okay with. Next, if you are above the threshold force, you should increase the recruit value. We accomplish this using this exponential function here. And so you have a growth parameter, which is essentially going to control how quickly recruit value increases as sensed force exceeds threshold force. And we take the floor of this in order to get nice integer numbers. Now, of course, you can consider a situation where the exponential function has exploded, as exponential functions do. And if you have a big structure and one robot over here has a recruit value of 100, a robot over here would get recruited, which would not really help, right? And so you introduce a maximum recruitment value factor parameter that will limit, of course, the maximum value of the recruit value. And of course, if you see a neighbor with a higher recruit value than you yourself are calculating, that value takes precedence so that you can propagate and decrement recruitment values. Having explained reactive build, I then had to simulate it in order to validate that it works. And so to do this, there was a bespoke simulator in MATLAB that I wrote. The goal here is for the simulator to be fast while being reasonably accurate. In total, we had about 92 total sets of trials, each of which had 100 runs of 100 robots each. And even with the optimization we did, it took about 10 hours per run. The primary optimization that we did is that forces are only recalculated after a robot joins the structure. So as a robot is climbing up the structure, we ignore the forces that would be applied by that. The forces themselves are calculated using the finite element method. If you're not familiar, it's essentially a way of going from a given configuration, turning that into a big matrix math equation, which you then solve. And from that, we get essentially two types of values. We get the in-robot forces, so that's the actual force sensor measurements. And we get the between robot forces, which are really what we care about. It's the forces at the connections between the robots. The target platform for this, the platform that is being simulated, is FireAnt 3D, which I presented in IROS 2020. This robot has been shown to climb on floors, walls, and ceilings of its peers, and we anticipate that future iterations of this robot will have all the capabilities required from Reactive Build. So, we have the simulator, we have the algorithm, now I have to validate Reactive Build. There are basically two goals here. One, have to demonstrate that it works, of course, and also we want to understand the impact of the various parameters that I talked about before, namely growth parameter, the rate at which the recruitment value will increase as sensed force increases, threshold force, which is the minimum force to start recruiting, and max recruit value, which is the maximum value that the recruitment signal can take on. The first structure that we demonstrate here is the tower. And so, as you can see from this video, it worked. Reactive Build built a tower. And what we saw here is that threshold force was the most important parameter to control tower growth, with changes to the growth parameter and the maximum recruit value being less important and being indistinguishable from actually changing threshold force. One thing that we did see that was pretty interesting is that the threshold force, was linearly related to the final peak connection stress. So after 100 robots had been added to the structure, the maximum connection stress among all the robots is measured, and we have a nice linear relationship between threshold force and the average final peak connection stress across those 100 trials. Another thing that we saw was that the height of the tower, so the basically position of the highest sphere of the highest robot, grew with the square root of the number of robots. If reactive build were causing robots to simply build a given shape and scaling it along all three axes equally, you would expect this to be the cubic root. However, because it's the square root, it implies that as the tower grows, the robots are able to use reactive build to actually change the sort of shape, sort of tower that it's building. The second structure that I am demonstrating here is the chain. And so as you can see, there's an arena and they dangle from that. Once again, threshold force is the most important parameter. And once again, we have this nice linear relationship between threshold force and the peak connection stress. Qualitatively, one interesting thing to note is that as the chain grew down, eventually the need for support was such that you would start having robots actually kind of creeping up on the arena itself in order to provide enough support, which then they would require their own support. And so you would have kind of a runaway support growth that would prevent further chain formation. The final single origin structure that we're looking at here is the cantilever. Once again, it worked. Great. And threshold force was the most influential parameter. Once again, threshold force is linearly related to the final peak connection stress. And much like the chain, we see the growth of a support structure that actually ends up stopping further growth of the cantilever. And I want to take a moment just to compare the final connection forces between the tower, chain, and cantilever. Notably, the tower and chain have extremely similar results for the threshold force and final peak connection stress, with the cantilever being a bit higher overall. This is not terribly surprising. In general, cantilevers are challenging structures to build. But what these trends show is that the final peak connection stress is predictable based on threshold force. And so what this implies is that you're going to be able to scale threshold force based on robot capability. The final structure we're talking about today is the bridge. And so with the bridge, it's a bit different since the goal here is to have one robot go from the left side to the right side or vice versa. And so for this, there was no alignment or communication between sides. And the only special thing about this experiment is that robots on the left are targeting a location on the right. Robots on the right are targeting a location on the left. Otherwise, there is no special behaviors for the robots to build this bridge. Threshold force was, again, the most influential parameter in terms of determining success rate, where we define success rate is within 100 robots, was one robot able to successfully cross that bridge? However, we also see that growth parameter and max recruitment value are in fact very important for bridge growth. As you can see here, lower values of the growth parameter result in higher success rates, significantly so. And the same is true for the maximum recruitment value. Qualitatively, certain bridges failed as a result of the runaway support structure stuff that we talked about with the cantilever. Makes sense, basically two cantilevers that meet in the middle. But we generally saw three types of bridge. The first type of bridge is a separated cantilever, so you have a small gap between the two that a robot can cross. You have narrow connections where you're touching on maybe one or two robots. And then you have the unified support structure bridges, where you have those big support structures kind of meeting in the middle and forming a very thick bridge. The causes of this are not something that we were able to determine through our experiments. And so the overall interpretation here is that Reactive Build worked. It was able to allow robots to build towers, chains, cantilevers, and bridges using a single set of behaviors. What we saw is that threshold force was the most influential parameter, and it predictably impacted the final connection force between robots after the structure had been built. The growth parameter and the maximum recruitment value were less important for the single origin structures. However, for the bridge, it seems that it's rather important to keep those as low as possible. To conclude, Reactive Build enabled robots to build robust structures simply through reacting to the environment. This allowed the individual agents to have a high degree of autonomy, and multi-origin structures did not require special behaviors. In the broader context of robotic self-assembly, Reactive Build satisfies a niche that has remained relatively unexplored, and which I feel holds great potential. In most papers on robotic self-assembly, the formation of a priori structures and latticed structures is treated as the default, with seemingly little consideration for the alternatives. It is my hope that the work presented here will inspire others to consider latticed versus amorphous and a priori versus environment adaptive structures to be design choices to be made when designing their algorithms. Amorphous and environment reactive self-assembly holds many potential benefits yet to be explored. Thank you all for your time. Again, my name was Petrus Swissler. Feel free to contact either me or my advisor, Dr. Michael Rubenstein. This was all funded through NSF, and thank you very much for coming.